upcoming NOAA Atlas 15. Upcoming might mean a couple of years. I don't know how much longer yet, but Dave's on the front end of a lot of that work, which feeds into this process. So thanks a lot for being here, and look forward to the presentation.
Thanks, Paul. Yes, so NOAA Atlas 14, the previous version, is so it gives estimates of what extreme precipitation is going to be like. So like 100-year event, 10-year event, they sort of set the standards. And now they're beginning the process of doing Atlas 15. And this is just one component of that. A lot of Atlas 15 will involve the historical record. And this is just future projections so that they give a sense of how things might change. So like the method I'm going to be using is statistical downscaling. So you find a statistical relationship between the large scale, so usually like a reanalysis, a grid reanalysis, and then the weather station data. And then you apply it to the climate models. So first you would have to debias the climate models to make them like the reanalysis, because that's what you trained your thing on. And then you would apply the statistical relationship to the climate models. And this is just a general case, so I'm going to be focusing on precipitation in this talk, but it's easiest to think about temperature. So for the first few slides, I'll be looking at this. So this is just a hypothetical. This is not even real data here. So you like imagine you have a regional scale predictor. So like this is like temperature from reanalysis, and then this is the temperature at a weather station. And you'd hope there'd be mostly a linear line because these variables there are supposed to be the same. But of course, no fit is perfect, so there's noise. So like typically, in a lot of cases, you'll just use the linear fit. And so like if the precipitation is 12, if the temperature is 12 in your reanalysis, you would just use this value here, just run up to the purple line. And that's your deterministic, that's your temperature prediction. And that's your most likely situation. But again, if you just use the purple line, you'll underestimate the variance. So if R is the correlation between these two X and Y, then the variance of the signal that you predict from your downscaling will be reduced by a factor of R squared. So like in order to preserve variance, you need to just add noise. So there's this unexplained component of variability, and as far as from our perspective, it's noise. And if you want to give the most realistic representation and downscaling, you need to add noise back in as sort of the right shape and right character as the component you were not able to predict. So like in classic linear regression, that assumes that the noise is Gaussian, and it assumes that the spread, the standard deviation of that Gaussian, is just fixed. It doesn't change. It doesn't depend on your predictor here. So for precipitation, we use the same general idea. There might be some most likely value that you expect, but we're going to have a PDF, and it's not going to be Gaussian, but it's going to be a PDF. So so for precipitation, it's kind of easiest to divide it into two steps, sort of two models that you're going to use to downscale. So one's with a model that's just yes or no, is it going to rain today? And then the second component is if it's a wet day, then what's the distribution of precipitation? And this is sort of what you're up against here. So this is, I think, Madison here. And this is just a histogram of the precipitation amount. And you can see that the most likely value is like 1/100 of an inch, smallest measurable value. But then there's this huge tail going way out. So for the occurrence is what we call the precipitation occurrence, the model, is it going to rain or not. We're going to use logistic regression, And there's all sorts of more sophisticated machine learning methods, but overall we found, given the limited record, this kind of works the best because the records only say 60, 70 years or so. So what this is just an extension of linear regression. So you have your predictors, x, x2, and so on, and you're still going to combine them in a sort of a linear way. And then it's only the last step you're going to run it through this logistic function. And that's plotted down here. So as your input ranges from infinity to negative infinity, this keeps it between 0 and 1. So physically what it is just a probability. So the logistic regression, you either use a linear combination of the predictors, and then you feed it into this function and makes it like a probability. And when we do it like this, where we feed it a 1 for a wet day, a 0 for a dry day, it would be the probability of a wet day when you do this thing. And then to generate like data, you would then just draw a random number, and if it's less than your probability of that day, then it's a wet day. Otherwise, it's a 0 day. And so sort of a two-step process. So the fundamental thing is a probability for each day, and then to generate data, you can just draw random numbers if you want a user who's used to working with actual data. So for precipitation amount, we're going to use this distribution called a generalized exponential distribution, and if you're familiar with the gamma distribution, it's essentially the same kind of thing. It's just easier to work with because it's invertible CDF. So basically, it has two parameters. One's a scale parameter. So if B changes while A is fixed, it has the exact same shape. It's just determining how far off the origin it is. And then there's a shape parameter, which is demonstrated here. So for a small shape parameter, the distribution goes peaks up at 0, and then it decays away. And for like shape parameter 2 or 3, it will actually the most likely value will be it's shifted off the origin, and it will go down to 0 here. And for A equals 1, that's the same as exponential, an exponential distribution. So it turns out, just looking at like scattergrams between your predictors and the actual precipitation, it appears that the best thing to work with would be the mean of the distribution. So the mean is related to A and B with some function, but basically what we're going to do is we're going to predict the mean of the distribution, and sort of based on our logistic regression ideas, we're just going to have the mean be a linear sum of predictors, and then we're going to do the same for the shape parameter. We find that this shape parameter also varies with your large scale. And then once the mean and the shape are known, then there's just a formula for B. And then there's one little issue, is that linear doesn't work because these parameters have to be greater than 0. So we use this function in the machine learning literature. It's called soft plus. So it's it's linear when your argument's positive, and then it smoothly shifts to being bounded by 0. And we do a little parameter here which adjusts how quickly it adjusts. So K is small, then it will be almost like a kink here, but not quite. And K is bigger, then it's more smooth transition. And we just use a fixed K to find one that's reasonable and don't touch it again. So predictors, so we're going to use the ERA5 reanalysis. And the ERA is quite good and high resolution. It's not actually kind of like a climate model in some ways. So what we do is we're going to smooth it so that it's like the coarsest climate model. So just with like a Gaussian kernel, and just smooth all the data beforehand. And then the most important predictor is precipitation. And sometimes people are kind of surprised, oh, like precipitation is really bad. And yes, it's bad, but it's like, it's still the best thing, apparently, so that's the main thing. You really need that to help improve scale. And then we also use the wind field, and then we have an orographic precipitation model. It's based on this paper, which is a really interesting paper actually for understanding the dynamics of orographic precipitation. So it's basically, you have flow running over some topography, and then the dynamics is just gravity wave dynamics, where it sets up a gravity wave field which determines where the flow is going up and where it's going down, and it actually selects certain scales. So like if you look at the details of PRISM, which is just pure statistical, when they're dealing with precipitation, they smooth the topography with like I forget the exact number, but like a 5-7 kilometer smoothing. And this was sort of naturally does it on its own based on the dynamics. But the one little thing that's maybe not the best is they made it linear, which is good for understanding things. But for the precipitation process, that's a little too crude, so I just tweaked that aspect and made it so like the air has to be saturated before it starts condensing things and things like that. So this is an example for a station of what we get after we fit our logistic regression, we fit our gamma distribution, and what this is February 2019, this is the 8th through the 24th. So each of these little boxes is a day, the 8th, the 9th, the 10th, the 11th. And the blue bar is what happened on this scale here. So here's millimeters. So when the blue bar is right here, that day it didn't have any precipitation. And here it had a small amount, and here it had a larger amount. And then the red is a PDF that we get from our method. So again, it's not deterministic. We have a range of possibilities, and this is what our guess of the PDF is based on our statistical fits. And then there's one more component of the PDF that's relevant, and that's the probability of precipitation for that day. So like there's a 98% chance there, then 1%, and so on. So you can sort of see, and some elements are kind of doing the right thing here. Like for example, this is a very wet day, and this is a case where the PDF doesn't peak at 0, unlike the aggregate. The aggregate total PDF peaks at 0, but here it's pushed it off to 0, and it's, so it's just like it's sort of supposed to be, although you can see it's very broad again. And then you'll see some days where it rounds to 0 probability of precip, and it was 0, so that's good. But then you'll see other cases where, like for example, this day, this PDF is not as extended as far out as the next day, but oh wait, but the actual precip was bigger on this day than here.
I'm sorry, what fields are going into making those PDFs? Like what from the analysis you're downscaling?
Yeah, so this is so these are our predictors
So
from the real analysis,
precipitation.
and they're determining these coefficients, like an intercept term and a weight term for precipitation, a weight term for the wind, for the U curve of the wind, the weight for the wind. And so for logistic regression and this sort of regression, we just maximize the likelihood of the statistical method that we use to fit things. And it's also things have been cross-validated where this hasn't seen this data here. So anyway, so what you're getting out is parameters of a PDF, and then you just plug them in your PDF and just plot it out.
Mm-hmm.
So, just on those predictor variables, you've got wind and you've got the output from that orographic model. What do you think for output from that orographic model? Just precip?
Yeah, so the output is precip, and then there's a little filter where the orographic model has to have a certain standard deviation as far as variability in order to be used, because I don't want it to be used. I mean, it will output tiny values wherever, because there's a little bit of slope, and it will sort of make them very important if it sort of latches on to some variability that's there and it's not really physical, so.
So like in Madison, you would be
Yeah.
using the orographic model.
Yeah.
What about like, so does and you said winds are also incorporated?
Yeah.
Does it like, so lake effect, are
That's
winds-
that's the hope. I mean, I haven't had much time to really analyze. There's, yeah. So then, now we're gonna get to the interpolation to the grid. So like, as of now, everything's being done at just one station. And then the another station nearby is just another statistical fit. Everything's, just independent. So now we need to sort of blend it. And what we end up using is kriging, which is great in some ways, but kriging is like finding your weights. So you have this grid point, what's the weights of the stations around to, give you the value at the grid point. And sometimes the weights can be negative, which is sort of how it extrapolates. Like if you can imagine, you get these precip increasing, and then you want to know what the grid is out here. It can extrapolate with those negative weights, but we don't allow that because of precipitation. And besides, I think probably the better way to extrapolate is with the prism. So prism has the advantage that they're just finding a climatology, so you don't need that much data compared to doing a regression, which is what we're doing. So there's many more stations in prism, and so we use that to extrapolate, where like essentially we're interpolating the fraction of the climatology at a given day, and then we can bump that up based on what the prism is at a grid point that's away from the station. It's just based on how the prism climatology bumps up as it goes away from the station. And then there are some issues with how interpolation is usually performed. In some cases, like observations, there's really no way around it, but for our case, we can actually take advantage of our probabilistic method and actually do this in a better way. So for example, imagine just a situation where you just have two stations, and then you want to have a grid point exactly in between. And I don't really know any other interpolation method that want to assign equal weight to each of these stations to give you the value at the grid point. So like, say station 1 and station 2 have the same variance, then the variance of at the grid point, which is just half of station 1, half of station 2, is 1 plus r over 2, where r is the correlation. So like for example, if your correlation is 1, then the variance at the station is the same as the station's 1. If the correlation is negative 1, well then that's 0, because your stations cancel. But if like you have a typical case, say r is like 0.7, 0.8, especially for precipitation, which can vary really strongly at high frequency spatial scales. So this r can be actually quite a bit smaller than 1, even if it's it's still over a half or 0.6. But so what you'll end up doing is your grid point variance and your extremes at the grid point will be reduced compared to the actual stations. And another downscaling, gridded ground scaling product is LOCA, and they use gridded precipitation. So here I could show like some of the pitfalls of doing this approach. So what they did here is, these are the stations that they used, and they calculated what the 20-year event is. And that's plotted here. And then this is the 20-year event in 2 versions of the gridding. This is the latest version of the gridding. And I don't know if you can see so well, so I blow it up here. So this is the 20-year event in the gridded product, and you can see little bullseyes. And in other regions where the 20-year event is not as big, and what's going on here is that the little peaks are where a station is. So you're right close to a station, so the weight is almost all 1 at that station. Whereas like if you're between a station, then you're gathering a bunch of partial weights at nearby stations, and because that station variability, those stations aren't correlated so well, especially for precipitation, you end up damping the extreme. So the variance is, where the variance is weak is where you're away from the station. And if I go back, you can see some of the greens go all the way up to Iowa, and the greens go all the way up to along the coast in New England. But if you look at the extremes here, the greens actually stop down in Missouri, and they only maybe go up to New Jersey. So you can see again, just by the gridding process, you damp the extremes, and that's because you're just, the only way to not do it is to do nearest neighbor interpolation, but that of course has other issues where all of a sudden, like, you know, you're just picking and choosing one station, even if you're almost as close to another station. So the way we're going to do it is we have sort of a special case where we can do something different. So instead of calculating precipitation at each grid point by like drawing random numbers, etc., what we're going to do is actually stay in the PDF space, and because our PDFs are determined by the large scale, they hardly vary from point to point. So like you could have Madison and Dodgeville, and the point in between, the PDF parameters at those 2 points are almost the same. They're varying in tandem because it's forced by this large scale reanalysis.
Sorry, I'm a bit confused. Just be sure I understood right. So what you're doing there is you, instead of fitting the fitting the precipitation on the spatial scale, you fit the coefficients of the predictor that go into the PDF.
Yeah, so it's like we have the coefficients of the PDF at each grid point.
Yes.
And then they're slowly varying, and so what it means is that there's really not really any detectable. It's so negligible that you can't really tell any damping of extremes away from grid points. So this is the map for the downscaling, the 20-year event. And you can see the greens go all the way up to Iowa, they go all the way up the coast, and then along the Gulf Coast, you get the biggest extremes, and you can see that's the actual data is like that too, where you get up to these dark blues. So it's because we did the PDF approach that we can kind of do this and kind of have a really statistically uniform gridded precipitation instead of being more extreme by stations. And then here's an example of the 100-year event, and the top is Atlas 14. For some reason, Atlas 14 didn't get to these two states yet, so blank. And here's the downscaling. And there are some issues. In many places, this is actually slightly too extreme, but overall, it gets the general patterns right. I was not aware like how extreme precip can get in the Sierra Nevada and along the Cascades. So those events are quite big, almost as big as down by the Gulf Coast.
How does Atlas 14 do the interpolation?
So I believe they would just do all the statistics at the station.
For like the 100-year event, you
Yeah.
can generalize extreme
Yeah,
value distribution.
they would do it. Yeah, so they would do all the statistics at the station, and then the last step you interpolate. So that's another way to not have these issues with gridding. And again, I should mention these are just done totally different ways. So like for Atlas 14, there's two different ways, but this way they just take, if you have a station, say it's 60 years long, you just take the maximum for each of those years. So then you just have a time series of 60 events, and you fit that to an extreme value distribution. And it's amazing it works, because you just basically chop down all the data, and that's how you do it. And then this, again, is just taken from all these daily PDFs. Apparently you can actually calculate it from the PDFs directly. And
So would you say that so is
I
your estimate more reliable?
No, I don't think so, because like I'm trying to get every detail about the daily right, and here you kind of have it easy. You can just not, like I want when I throw something out that gets this right, but it's not really doing. There's so many ways it could go wrong with the daily, so I'm so focused on the daily that you could see this being better because it's just it's just target. It has just one goal, to get the extremes right, whereas I'm trying to do regressions on all data. I don't know for sure, but I think that's probably correct. It'd be definitely something to look into, like different approaches. And then here's an example for an individual day. So for gridded, observed, in quotes, I'm using this multi-sensor precipitation, which combines stations with radar. And then this is the output of the downscaling. So here's a map of the probability of precipitation for this day. And here's a map for, if it's a wet day, what's the mean precipitation of that generalized exponential distribution. And then this is the shape parameter. And one thing you'll notice is that the shape parameter sort of goes up with the amount of precipitation. So a high shape parameter, remember, is when the PDF shifts off the origin. So low shape means the most likely event is like near 0. And then as you get to above 1, then it's off, and then the most likely value is off 0, and it keeps getting more and more as the shape goes up. And so you can see overall it's getting, so this is like, I think, Tropical Storm Lee, the remnants of it were coming up. And you can see it gets essentially almost 1 probability of precipitation. And then I guess that's some monsoonal stuff. It has weaker probability of precipitation. That sort of goes with like what's going on in reality. And then to make real data, though, we need to somehow draw our random numbers from the distributions. And you don't want to just make them independent of each other, like this grid point and the next grid point. You don't want them to be independent, otherwise it will just be speckled noise, not look realistic at all. So what you do is you smooth them in space prior to using them. So you draw random numbers, and if you do something additive to them, then you preserve a Gaussian distribution of the noise. And then you will, another little thing is that I smooth it anisotropically, so along the direction of the wind at 3 kilometers, there's more smoothing in that direction, sort of gives the streakiness of the precipitation field. So then after that, you transform that Gaussian distribution to the actual distribution that's estimated from the downscaling. So this is an example. This is the same as the previous slide, and the same with these. And then here are 3 realizations, is what I call them. So just draw random numbers, and there's sort of like all equally likely situations given the PDFs. So you can see, there's quite a bit of variability between them. They're all preciping here, but there's quite a bit of different strengths. And actually looking at the monsoon area, this one is very widespread precipitation. It's very weak and local, and same here. So again, based on the ERA5 and what I've done, this is like, these are all equally likely situations given what we know about the large scale. And then for fun, I looked at Hurricane Katrina. And again, I guess I should mention, I'm applying this is doing it based on ERA5. I haven't done a climate model yet. So anyway, this is just when it's just starting to come in. And this is like the probability of precipitation and how wet it is if it rains. And then here's the 3 random realizations. And things get a little more easy to see the next day. So here's the actual precipitation. This realization is actually a little bigger, but then the other 2 are weaker. And then here's the next day after that. You can sort of see, again, there's definitely correspondence. So you can pick out which day is what based on realization and the observations, but there is quite a bit of scale. You know, just having the large scale, it only tells you only a portion of what's going to happen. Okay, and then here's an example from a climate model. In this case, we don't have any observations. This is the climate model precipitation. And then these are 3 realizations based on that climate model. So of course, this is one input, but then there's the other inputs, the wind and the orographic precip. And then I also show local downscaling for this day. And you can see it has the general features, and there's even some similarities, but it's like kind of splotchy, again, where the stations are. And it's also kind of, you don't really have any of the advective kind of features you sometimes get with real precipitation. And it's also not quite as extreme. Like the biggest events in some of the realizations, they just exceed this, which is consistent with, the statistics of the loci. So then here is but then this is just looking at the mean change for the end of this coming century. And here I averaged over all 28 climate models that have data here. And there are actually some, I'll go over the general features is during the cool season, it gets wetter in the north, like November to December, January, February, March, April. And then this is actually somewhat different than the way I remember the CMIP 5s. So like, overall there had been a tendency that the wetter places would be further north and the drier places further south. But here, the actual driest places in the across the northern U.S. tends to get wetter further south. And there's this area out here in the dry Intermountain West to California, which is quite dry. I mean, quite a bit wetter. And for reference, I'm going to show here the climatology. So this is the same. Here's the climatology. You have this quite a bit wetter as a percentage. This is given as so like 40–50% wetter. But that's actually it's a really dry part of the year for that time of year. So it's sort of like here's the monsoon, North American monsoon. It's sort of like an expansion, but the raw amounts might be kind of weak.
Dave, do you know why CMIP 6 changed in its July-August dryness in the northern part of the country?
That's a very good question. Yeah, there's been some studies about like the stationary waves have been done better and how they shift, and that might be key to like looking how, like the phasing of the stationary waves is really key for like where you're gonna get the moistening and the drying. But it's definitely something, really interesting to look at. And I guess the other thing I wanted to say is that some of the shoulder seasons are kind of like more iffy. There's no real clear sort of signal. And another thing is like this is very wet here as far as a percentage. But that's actually a dry part of the year too in the northern plains. They get a lot of their precip in May, June, and there it's quite a bit weaker. So this may look like you're going to get more precip, but it's really like it's not going to be as much because it's only weekly increasing in the time of year where they really get their precip.
So how are you using all 28 models? Are you using an average of all 28
So
models?
it's just an average, yeah.
downscaled?
And there's quite a bit of variability in some cases, which I'm getting to right here. So this is a fraction of models that have increased precipitation for each of these 6 times a year. So like 1 means that they all get wetter, and 0 means none get wetter, which is the same as they all get drier. So very consistent, like over 95, maybe all of them get wetter during this January to April time frame, and also the November, December. And then this was something that that's different than, we've done a lot of work locally with Wisconsin and what's going to happen, and this is kind of disturbing here. Before summer was sort of like a 50-50 thing as far as whether the models get wetter or drier, and now they're saying almost pretty consistent that it's gonna get drier here in summer, so that is, there are been some changes, and it would be really good to see like what are the large scale fields. That would be an excellent project to look at and try to get some understanding of what's going on. And then I think that's actually my talk, so I ended it.
Great, thanks very much, Dave. Any questions for Dave?
Yeah, so you're looking intermodal variability. Have you looked like within one model ensemble members? Like, does one model with the same underlying physics show as much difference?
Oh, yeah, that would be a good thing to look at. For me, I just did one ensemble member, so that would be an advantage of LOCA, because they do have as many as possible ensemble members, and that data is probably available to see. Like, again, with the mean fields, there's probably, this should be pretty consistent with that.
Okay.
Mike?
If you look at projected changes in extreme rainfall, is there much difference between your CPEP 5 and CPEP 6 downscaling?
I haven't quite gotten to it by season yet, so that's, yeah. But yeah, I'm also doing Hawaii and all these other things. There's been some issues with the extreme precip in Hawaii and getting that right, so I'm kind of behind a little.
I do have a question about the way you choose your predictor. I just wonder if you like just put the raw variable, or if you also like include combination of variable, like I don't know, wind time, something, or like even variable at previous time step, something. How do you choose like pick your predictor?
Yeah, so all of them are, it's 20, you're restricted to 24-hour means, because again, the climate models, all their data is like 24-hour mean. If you want finer temporal resolution, then the number of models you have is very limited. So I did the same 24-hour period when I'm doing the fitting, so I didn't use any like lag. But then I did try a bunch of different things like static stability and moisture and different fields, and then I looked at the overall scale over a large area region of stations, and the scale wasn't hugely different. Overall, the scale would incrementally increase as you added predictors beyond what I chose, but then there becomes the issue of like, I'm not really sure the best approach, but again, you have a station here and then the other station nearby is using a totally different regression. And if like using a lot of stations, it's more likely that one station will hook onto one set of predictors and then a nearby station will hook onto another set, and so you'll get more noise. And so there's sort of some compromise that, of like, how much skill do I want to have, but I don't want to go so far that like there's lots of randomness in the coefficients between different stations. And of course you can smooth that, but again, the whole goal of the downscaling is to get local climate differences, so I just opted to not do any. But again, there's definitely, with statistical downscaling especially, there's so many different choices, and really looking at them, it's a really good thing to do, but you're limited in each time you're doing it, but there's so many things to explore, things like I do blend and use more predictors, and so on.
I'm a little bit confused about some of the PDFs. It seemed like they provided values greater than one, so I'm just a little bit confused about that.
Was it the line plot or some of
Some
them?
of the line plots, yeah. Like, they seemed to, yeah. Well, these ones don't, you can't see the values, but.
Yeah, so I use the same range here. Some of them just go up, they go off.
But is
That
that
would
fine
mean-
when it goes greater than one?
It's some arbitrary value. The PDF that integrated over the whole thing is going to be like 100% minus 1%. So this would be 0.99. Like this one would integrate, wait, what was I saying? Oh wait, the probability precip is just 1%, so like integrating over this would just be, instead of being 1, it would be 0.001. It's the integral that should be consistent. So it depends on the width too. So like this one, when you sum over it, it should be 0.99 because there's still that 1% chance that it didn't rain at all. That's how it worked. And again, another corollary is like the actual value doesn't matter if it's really narrow, then the integral is still not, unphysical.
Can you talk a little bit about kind of what the goals of the NOAA Atlas are and what is going to go in there overall?
Yeah, so
Like, I'm not
probably
familiar
the
with that
biggest
product.
portion is probably the historical. So they are changing all the methods to do
They're trying to come up with better historical
better
estimates.
methods of doing it, and it involves also the interpolation too, and all sorts of things.
And so there's going to be multiple different products, or you're like competing to have your product in there, or how does that?
And then no, this is like sort of a second component of like how are things going to change in the future. And they're actually going to use, I believe, LOCA and one other downscaling project in these things. They probably just sort of just aggregate, get the most information from different sources to get the best estimate. And so it's sort of like two components. The historical, I believe, is just being done one way, just from one group, I believe. And this is just one of the components for future projections.
I thought the atlas included some daily with for IDFs, right?
Yes, and then they also do all the sub-daily and also weekly, like there'll be 100-year events for weekly events.
What is that used for?
It's like design, the stormwater infrastructure and
Zoning, where you build, where you,
call window.
Sizing infrastructure.
so it's a big deal.
Yeah, anytime anyone's building anything, especially stormwater, this is the source of,
Do you have a sense for how, sorry, I'm jumping in, but like, following up on this question, do you have a sense for how, like, are they gonna use time windows in the future for, like, how you use this? Because, I mean, your results are showing changes in expected changes in preset. And traditionally, I think it's all just been historical. So
Yeah.
how are people gonna use this as you're designing projects, like?
Yeah, I just.
Yeah, I just don't know if anyone, this is a broader
But
question.
maybe they think, well, you want something to last 100 years, and so it's actually some combination of what it is now integrated over the next 100 years. So like they'll use the whole scenario. Because like.
That would be
that would be
the
the
logical
logical
way
thing.
to do it, right? Is to
And
say,
it would
if I want
depend
this
if-
to last to 2070, what's likely happening in 2070 at the 100-year, 24-hour event, such that we can pass that amount. But that's gonna be
And if
That
you're
has
building your
potentially
building.
more expensive and larger, so larger and therefore more expensive, so it's not always politically motivated, right? I mean, to spend more money, so.
And like, let's say precip extremes are getting, more intense by the end of the century. But if you're building a 100-year event, it's actually, the probability of that 100-year event is slightly less because it's sort of an integral over now to there. So they'll probably take that into account. They'll do like little periods starting from, 1920, 1930 out to some X amount of years.
The challenge, of course, is that if I need to go design a culvert to go under a road, I have to choose a size. It's gotta be a 24-inch, 36, or 37, or 38-inch, right? I can't put in something that's gonna adjust in time.
Probabilistic.
Right, I can't put in a probabilistic. So this is all wonderful, but at some point,
Yeah, you need to
you
just.
have to put in one size of a culvert. I mean, that's the most basic example, right? But, so then you talk about, well, what's the uncertainty? You can make it large enough, but
And there are frameworks for how you do this. I mean,
Yeah.
the overarching question I had was more like, Atlas 14 has been used in a certain way for however long it's been around, and now this is a fundamental change if they're going to put some sort of a future change in the parameters that define all of this. And they haven't, like, no one's thought about it. I mean, I'm sure people have thought about it, but there's no established.
No.
Okay, so this is
It's
wide open.
quite a big group though, they're
Yeah.
looking at all, yeah, and a
So
lot of the
what
people that were involved
products are
with.
gonna go into Atlas 15 is still unknown, is that accurate, or?
I guess I was saying yes in response to how this will be used in
Yeah.
practice.
Oh, okay.
Yeah, like how, I mean, you could imagine that you incorporate a discount rate into future adaptation products into this, or I mean, there's this, and then there's all the framework you put around this for the future, but fundamentally, this is fundamentally different than Atlas 14 because there is a future change, which is not in Atlas 14.
We should invite the people that are, I know, I think we can invite them in 2 years to come and see how they're actually using the data and like what decisions and they decided to make.
Sorry, what, another question here, your future, if I'm jumping in front of you.
No, there wasn't any.
Okay, like your future projections, like in the previous versions of this, you had a generalized gamma distribution with that third parameter in there that you use to try and constrain future extreme precip. Is that still included in this?
So I glossed over some things. So what I did is added, instead of the other parameter, I have a mixture that I add another PDF. So it's a mixture of two of these, and it's just a small component that's involved with the tail.
Okay.
So technically, it's instead of being the 3 parameter fit here, it's again 2 parameters, which are the main thing varying, but then there's a mixture added on. It has the same shape as the fundamental one, but it's sitting out there to get tuned to get the tail, and it doesn't always get used. That's the one case where I do aggregate some stations when I'm looking at the extremes and trying to tune that second component of the mixture. So I would use all the stations within a certain radius. And you kind of have to do that for extremes, because like, you could just, this station and this station could be different, it's more likely that any differences are just sampling. And so for the extremes, you gotta aggregate. And that's what they do in Atlas 14 and 15. You can't just, the statistics are never just dependent on one station, even if it's like the longest station in the country, you gotta aggregate.
Does that mixture distribution take into account, I mean, does that like account for the fact that like in the, where you're seeing the highest precip amounts in the Gulf of Mexico?
Yeah. I should have labeled it, I forgot to
Yes.
label it.
Sorry. Does that take into account like the different physical regimes of summer hurricane season, tropical cyclone season versus?
Yeah, so I should have mentioned that each fit is done on each calendar month.
Okay.
With a 15-day buffer into the next, so it's like a overlapping 2-month periods that every fit is done. It's only at the very end that's sort of smoothed across. And that's important. I should have mentioned that. Yeah, you definitely don't want to just fit for the whole time. That's makes it more difficult. Maybe if you had machine learning, and again, I tried machine learning methods, and they were better when you aggregated stations, but then when you got to just one station, there wasn't enough data for them to outperform. And I was sort of surprised, because I thought I was going to use machine learning on an aggregate of stations, and then use that to sort of reduce the predictors just to one, and then fine tune it using the standard methods on the station, but that even did worse than just using just a straight up easier method. But that's, again, that's not really the final word, I don't think, but my first attempt didn't give something that was more skillful.
I was going to ask about that, how this compared to machine learning, so.
I think there's a way to do it, just the way I tried didn't work. Again, with statistical downscaling, there's so many things to explore. It's like, there's so many things that go into it, so that would definitely be something to look into.
Fusion models
There have been some researchers investigating the precipitation downscaling using some kind of hidden mark model or non-homogeneous hidden mark model. So I think the basic idea of that model is kind of similar to your downscaling method. So I think it would be interesting to compare the different methods.
So hidden Markov.
Yeah, it also simulates the probability of dry and wet days and also the
Yeah.
amount. And you can also include some predictors as you did.
Yeah, and so like with weather generator literature, they use it. Yes,
Yeah.
actually that was the original motive back, like, I hate to say, this is like way back, 2009 was the first time I did the downscaling. So like separating out into two sort of models, that was, I'd read some weather generator models, and they're there, so you get the Markov part because there is memory. And this is another interesting thing here, is that like, I didn't have to add extra memory because there's some memory, again, it's based on the large scale, so there's enough, the connection between the large scale and the station was enough memory, so that like, I can actually do noise that's totally different the next day and it's not unreasonable. But I'm sure as you get to finer scales, then you definitely would need to have the noise temporarily correlated. And for temperature, I do have noise that's temporarily correlated because, again, then you won't get the right autocorrelation of the temperature. But yeah, it's good.
So if I can just clarify on Lay's question, so there is no transition matrix from day to day in terms of precipitation?
Right. It's
But
all
it's-
internal to the large scale model. If I was not having any large scale model, I was just having a PDF, oh, absolutely you need to have memory, but there's enough, day to day.
Interesting, okay.
Like, I guess wish you could see that with like, Hurricane Katrina landfall, you have days going after each other, and you could sort of see that there's a lot of, correlation. Like here, it's high probability of preciping, and the day before it was also a high probability of precip, and then it was only the day before there was still some, so like you're getting this sort of memory just from the large scale connection.
Any other questions for Dave? All right, well, let's thank him again then.